Alright, welcome everyone. In this video we're going to do example number 2. These are my 16.7 extra problems. I think that they would be a fine level for quizzes or exams or timed assessments and whatnot. In my last video, we did example number 1, which was again a different type of surface integral over a scalar function. So our scalar function here was just nice old z. Here we have a surface integral over a vector field. That's right, because this is zk, so this is the same thing, right? There is no I or j component, so 0 and I, 0 and j, but in the k component there is this z factor. So in this video we'll calculate out the surface integral over this vector field for this given surface, and then we'll go ahead and interpret what we did and kind of compare this to our work in example 1. So okay, I have a page dedicated to example 2. Here's the example 1 work that we did. Here is our example 2. So again, we're going to calculate the surface integral. Our vector field in this case is the vector field 0, 0, z over the surface S, which is part of the paraboloid that lies inside of the cylinder, and we have to specify an orientation here. We're orienting upward. Okay, so a lot of the same surface work will be it's very similar to our first example here. So actually I'm going to cheat here for a second. I'm going to go ahead and just copy this. And if you haven't watched that first video, I highly recommend it. Alright, and now I'm going to go ahead down to our second example here. And theoretically I can just go ahead and hit paste. I don't do this stuff a whole lot. And we'll just try this one. Oh, it went down here. Alright, so I can just go ahead and highlight that and then move it up. So again, our surface is the part of the paraboloid. The paraboloid would go on forever, but it's only the piece that's inside of the cylinder. X squared plus y squared is equal to 4. So again, if you haven't watched my first video, I recommend that. That's where I actually describe how you can get the picture of the surface. Now let's focus on calculating out our surface integral. So again, our surface integral, this is the vector field 0, 0, z over this surface here. So again, I'm going to go ahead and set up some surface integral. Here we have 0, 0, z, so I'm going to go ahead and write it like this. That way you can clearly see each component and whatnot. And then this dot ds, remember this is dot and n, and then this is the regular ds kind of from the surface integrals over scalar functions, right? And so we have to remember n is a normal vector to this surface, and there's a couple different ways that we can find normal vectors. Either if you have a parametrized surface, right? So if you have some parametrized surface, maybe some r that depends on parameters s and t, then a normal vector would be either plus or minus r sub t cross r sub s. So something like this. So this would be a normal vector for a parametrized surface. In this case, again, our surface is given to us explicitly. We have z equals. So a long time ago in 14.4 we found out a formula, right, for normal vectors over some explicit surface. This is going to be plus or minus, and then we're going to have g sub x, g sub y, and then negative 1. Alright, so here's going to be our setup. So we have to decide here, should we have the, leave it alone, or we're happy with this, or do we want to apply this negative sign? So let's go ahead and do the setup, and then we'll talk through, how do I choose between this plus or this minus? Which normal vector do I want here? So again, we have 0, 0, z, dot producting with either plus or minus, and let's go ahead and calculate out g sub x. So our g function, that's what z is equal to. So take the partial derivative with respect to x, I get 2x. Take the partial derivative with respect to y, I get 2y. And here we have negative 1. Now, we have to go, in order to choose a normal vector, this is essentially given by the orientation. So in this case it says oriented upward. So oriented upward means that we have a positive z component. So in this case our z component is negative 1. Well, that is not positive. So in order to make it positive, I'm going to go ahead and select the negative and distribute to each piece. And when I distribute that negative to negative 1, that'll make it positive 1. So I'm going to go ahead and apply this dot product. Again, 0 times anything, in this case negative 2x, 0 times negative 2y, those are all going to be zeros. So I'm going to have 0 plus 0 plus z. And this is really z times positive 1. Now again, we're going to be integrating over some, xy region. So some region in the xy plane here. So that's why I have dA. So we're only going to have x's and y's, or maybe r's and thetas if we decide to do polar, but we're definitely not going to have any z's. So I need to go ahead and transform everywhere I see a z. Well, remember we were doing a surface integral on the surface z is equal to x squared plus y squared. So I'm going to go ahead and change that to x squared plus y squared. And now again, if we look at our region in this xy plane, we see it's a nice circle. So, well, I'm going to go ahead and evaluate this with polar coordinates then. So x squared plus y squared, that's going to be r squared. And then I'm going to have r dr d theta. And similar to last time, this region that we're integrating over, this is going to go from 0 to 2 and 0 to 2 pi, right, in order to get the entire circle there. Again, the circle here was given radius 2, because it's inside of the cylinder. X squared plus y squared equals 4, right? That's our radius squared. And we want the entire circle here. All right, so here's the setup. Already you can see, if you compare this to our last example, that we have a different setup, right? So the way that we interpret this really does matter. This is, again, a surface integral of a vector field over a surface. In comparison, example 1 was a surface integral of a scalar function over some surface, right? So again, what we're calculating out here, and we'll go into the interpretation here in a second, is fundamentally different than last time, right? The quantity that we get here will be different. It's representing something different than what we got last time. So let's go ahead and do the calculation. Again, we have nice constant bounds here. Our function only relies on r, so I can go ahead and do my theta integral very fast. We're just going to get 2 pi. That's integrating 1 with respect to theta and evaluating at 0 and 2 pi. And then when I evaluate out my integral for r, well, this is r cubed, so I'm going to have 1/4 r to the 4th. I evaluate that from 0 to 2. So when I plug in 0, of course I get out 0. When I plug in 2, well, 2 to the 4th would be 16. Divide that by 4, that's going to be 4. So altogether I get a positive 8 pi. So my final answer here is a nice positive 8 pi. So we can actually see, in comparison to our last problem, right, this integral was much, much easier. Another distinction is that we use just the normal vector itself instead of the magnitude of the normal vector. Notice in our last problem back here, because we had a scalar function, z, right, we used the magnitude of the normal vector. So the first component squared, second component squared, and then -1, the third component squared, all under our square root. Here we did the dot product along with this vector field. So we dot product it with n. So we can see that the calculation is different. Also, what we've calculated, right, this is fundamentally a different quantity. So again, the best kind of interpretation maybe for these surface integrals of vector fields over a surface is going to be flux, right? How much has a vector field helped push particles through a surface? And so in order to illustrate this, I actually got out the Monroe 3D Calc Plotter, and I've plotted this exact situation here. Let me go ahead and bring this up for us. So, okay, I went ahead and I just did the parametrized surface just so that way I could cut it off at the right spot. So this is the part of the paraboloid that lies inside of the cylinder, so you can kind of see its maximum radius here is 2 in each one of these directions. So here's the part of the paraboloid, and I wanted to calculate out upward flux, right? So I oriented this upward. And so the question is, does this vector field help push things in this direction, or is it pushing it kind of in the opposite direction? Is it pushing downward? Well, here is our vector field. Again, 0, 0, z. 0, 0, z, and let me go ahead and plot this. So here's what our vector field looks like. Again, there's vectors at every single point here. And we can see, well, it looks like that the stuff that actually is acting on this surface, right, although the vector field is pushing downward down here, right, there is no surface down there. So it looks like when it's actually getting near to the surface, it is pushing in this upward direction. It says it's trying to push these particles upward through the surface. So overall, right, what is the upward flux? We would say, well, it's helping push particles in this upward direction. So it's helping, so therefore we would expect that we would get a positive number. So in this case, again, we got the answer of 8 pi. There it is. So this kind of matches with the picture that we had here, that it was helping push in this positive z direction, right, in this upward direction, right? It was helping push particles through this surface. So we should get a positive upward flux. So again, here when we do a surface integral of a vector field over a surface, right, we get flux. So this is how much is this vector field having pushed through a surface. Here we were getting something kind of fundamentally different. We were getting kind of, I talked about maybe mass from density, right? So maybe your density is relying on the height of the z component of the surface. And so when you add this all up, you get mass, right? When you add up density, you get mass. So again, we got a positive number relating to some mass, but again, kind of what we're calculating out is different. Alright, so I hope you found these videos useful, kind of explaining the two different types of surface integrals that we have. So surface integrals of vector fields or surface integrals of scalar functions over a given surface. And hopefully this has helped, put together all of these ideas before our upcoming quizzes, finals, stuff like that. So, alright, thank you very much for watching. I'll see you guys next time.